Albert Einstein, Boris, Podolsky and Rosen proposed a thought experiment on the concept of quantum entanglement. This led John Stuart Bell to find what we know today as the Bell inequality or Bell's theorem. The Bell inequality and Bell's theorem are very famous but hard to explain without using difficult math. But this is physics made simple. I'm going to illustrate Bell's theorem with a spin-the-wheel toy and two ways to play the game, so you can get a clear understanding of the physics behind Bell's theorem. Let's get started. Particles are entangled when they are generated, interact, or share spatial proximity in such a way that we cannot describe their quantum states independently. The typical representation of entanglement looks like this. A laser is sent through a crystal. High-energy photons can split into pairs of two low-energy photons with perpendicular polarization. This means that if one photon points up, the other will point down, so their states are entangled with each other. Einstein, Podolsky and Rosen propose a thought experiment where we create two entangled particles, for example with the system above. We then move the two particles very far apart. Here we observe something fascinating. Particles are in a quantum state. Like with Schrödinger's cat, we can only know if it is alive or not by opening the box. As long as we don't look, the cat and the particle are in an unknown state. If we measure the property of one of the particles, the other one immediately adopts a defined state as well. But we haven't measured the other particle, and they are so far apart that the information would have to travel faster than the speed of light, which in theory is not possible. There are two ways to explain the observation of quantum entanglement. The first explanation is that the information traveled faster than the speed of light to the second particle. This explanation was criticized by Albert Einstein as spooky action at a distance. The quote became famous because it summarizes so well what we observe. But let's consider also the second explanation of quantum entanglement. The second explanation is that there is some hidden information that predetermines the result of the measurements before we performed it. The second explanation used the assumption of realism and locality. By realism, we mean that the property exists whether we measure it or not. It is just there. And locality means that the information cannot travel faster than the speed of light, and particles are only influenced by their environment. If the second explanation is true, then it means that quantum mechanics is incomplete because it doesn't entirely describe the particle's properties. This is what we call hidden local variables. John Stuart Bell improved this line of thinking with the Bell's theorem. If we perform independent measurements on each particle, then they each contain hidden variables. Because they each contain half of that information, it creates a constraint on their correlation that is known as the Bell inequality. But Bell then shows that the quantum physics that we observe with experiments violate this inequality. The correlation we observe in experiments doesn't match the constraints that he computed if we had hidden local variables. Since we see that quantum physics works with our experiments, something must be wrong in the reasoning. The only way to make the Bell inequality work is to assume that the hidden variables of the particles are not local. There is something that lets particles interact instantaneously with information traveling at infinite speed. This is the spooky at a distance property that Einstein was criticizing. But many people have tested this finding by measuring the properties of entangled particles, and they observe that yes, it doesn't seem that particles have local hidden variables, because the rule John Stuart Bell found for correlation with the Bell inequality would be respected, and it is not. Now let's illustrate how this works with a spin-the-wheel toy. Let's say I have a spin-the-wheel toy, and I'm playing with Albert and Marie. They have to guess on which half of the wheel the spin will land on. The trick is that Albert and Marie each get to decide how to split the wheel. They pick an angle to represent their choice. So basically, if the spin lands within 90 degrees of that angle, so half the circle, they win. In the easy cases, they can both choose the same angle, so they will always win together or lose together. They can also choose opposite sides with angles different by 180 degrees. That way, there will always be a winner and a loser. And if they pick angles 90 degrees apart, the wheel is then split in 4 parts. A quarter of the time you both win, a quarter of the time you both lose, and half the time there is one winner and one loser. This is simple, but it gets tricky. Bell's theorem tells us that reality doesn't work that way. In particular, it says that the amount of time you both win or both lose together is not exactly the same as the amount that you always overlap. Let's change the game a little bit and include some strange rules. Instead of spinning the wheel, I hide the wheel and wait for Albert or Marie to ask me for the result. Marie comes and asks me if she won. I flip a coin, and if it's head, I tell her that she won. If it's tail, I tell her that she lost. So my answer is random and unrelated to the wheel. I haven't spun the wheel. But now Albert comes and asks me if he won or lost. I look at the wheel. If I told Marie that she won, I consider Marie's angle to see if Albert won, not his angle. If I told Marie that she lost, I consider the opposite angle of Marie's angle to see if Albert won. Because I'm not using Albert's angle, the results are different. If Albert and Marie had the same or opposite angles, the result would match, and there would be no randomness. If there is a difference between the angles, the result would partially match. There is a correlation. These are strange rules, but experiments in physics show that the reality works with the strange rules. The state of the spin the wheel toy and Marie's choice of angles are the local hidden variables in Bell's theorem. The Bell inequality shows that while the game appears to work like that, there is no hidden spin the wheel with information, and information seems to travel instantaneously between the two particles. It is spooky at a distance, as Albert would say. This is an essential observation for quantum physics that doesn't solve everything, but it states one more time that there is no true reality that we could perfectly measure if you knew everything about it. Uncertainty is real, and the phenomenon of entanglement is real, and it is not due to some knowledge we don't have about the particles.